Okay, some background we need. Let's say that we have some curve. Generally, we're going to call the curve C. It is defined by R of t. So R of t is called the position function. A few things I want us to know. The first thing I want us to know is that the direction of motion. Alex, didn't I give you explicit instructions? No, it was anyone that's late. Okay, direction of motion at time t is in the direction of the unit tangent vector. Why are you all late? Do you not value my time here with you?
There was like a few of us going in at the same time.
Right, it's obnoxious. You all shouldn't have done that. I will tell you, my least favorite day of the year is Color Day, just so you all know. I hate this day. Let's get through notes, and then we can talk about why I don't like to do that. Because if I start now, that's what we'll talk about the rest of the period. Okay, second thing I want you to know is that speed is ds dt. What does S stand for? Well, I was expecting you to say speed, so I'm glad we didn't say that. Arc length? Yeah. So it's the instantaneous rate of change of the arc length traveled. Okay, one thing to note is ds dt is a scalar. What I also want us to know is that the velocity vector, which is v of t, that's going to be ds dt multiplied by the unit tangent vector. Now that should make sense. The unit tangent vector gives us direction. ds dt is the speed, so it tells us the magnitude. So this will tell us the direction and then the magnitude. That'll give us the velocity vector. V of t points in the direction of motion. And has magnitude equal to the speed of the particle. So lastly, if R of t is the position function, the way you find velocity is you take the derivative of the position function with respect to t. The way you find acceleration is you take the derivative of velocity with respect to t, which is the same as taking the second derivative of the position function with respect to t. And speed is ds dt. Practically, how do I calculate speed? Any ideas? What is speed most closely related to? Velocity. So you guys remember velocity has a direction. And so speed is the magnitude. It doesn't have the direction, though. So to find speed, you're taking the norm of velocity, or the length of velocity. So let's do some examples. A particle moves along C. C is the vector value function 2 sine of t over 2, comma 2 cosine of t over 2. Two parts to this question. First part, I want you to find the particle's velocity acceleration and speed at time t. Sorry that my handwriting is so crooked today. I also want you to show that the acceleration vector, bless you, is orthogonal to the velocity vector. That's in this case for this specific vector value function. That won't always be the case. Our velocity vector is going to be when we take the derivative of the position function. So take the derivative here by the chain rule, you're going to end up with a 1/2. So we get cosine t over 2, and then negative sine t over 2. Acceleration is when we take the derivative of velocity, which is the second derivative of the position function. Again, you're going to have the chain rule here with that 1/2, so we get negative 1/2 sine of t over 2, and then negative 1/2 cosine of t over 2. And then lastly, the speed is going to be the norm of the velocity function. So we get cosine squared of t over 2 plus sine squared of t over 2, which gives us a speed of 1. I could ask for the velocity, acceleration, or speed at a specific t value, like t is pi, t is 0, etc. You would just plug in 0. B, how do I show that acceleration and velocity are orthogonal? I would do the dot product, personally. And when we dot them, what should we get? 0. Can you see that you do in fact get 0? Yeah. Great. Any questions on that one before we move on? No? Okay. Okay, next example. An object moves in 3 space. So that its velocity function is 1t and t squared. Find the coordinates of the particle at t equals 1, given that at t equals 0, the particle is at -1, 2, 4. Okay, if we're finding the coordinates of the particle, we're looking for r. So we're given v. In order to find r, we're going to have to take the derivative of v with respect to t. Or, sorry, the integral. So we are going to need to integrate 1t and t squared with respect to t. We've done this before. You're just going to integrate each of those pieces individually. So if I integrate 1, I get t. If I integrate t, I get 1/2 t squared. If I integrate t squared, I get 1/3 t cubed. Now, anytime we did an indefinite integral, what did you have to remember? Plus c. And remember that c is a vector. At 0, the particle is at -1, 2, 4. When I plug in 0, I get 0, 0, 0, plus c. So that tells us that c is -1, 2, 4. Our r of t then is going to be t minus 1, 1/2 t squared plus 2, and 1/3 t cubed plus 4. We specifically are asked for the position of the particle at t equals 0. So if we plug in, or t equals 1 rather, if we plug in 1, we get 0, 5/2, and 13/3. Please make sure that you pay attention to the format of your answer. You're asked for the coordinates of the particle, so that's a point, not a vector. Okay. Questions? We're going to do one more example of this type before we move on. Well, it's kind of this type. Okay, an object with mass m that moves in a circular pattern with constant angular speed You guys know what that symbol is? Omega. Yeah, omega. So constant angular speed omega has position vector r of t equals a cosine of omega t times I, add a sine of omega t times j. Find the force acting on the object. And show that it is directed toward the origin. Bless you. Okay, so here's what we have going on. We have some object that is going around this circle. We have some radius vector. And then we have a constant angular speed. Okay, so obviously this involves physics, which you all know is not my area of specialty. What law does this involve? Force. Newton's second law. So F of t is equal to m times a of t. Okay, so in order to use Newton's second law, we're going to need to find acceleration. We know that r of t is equal to, like I wrote above, velocity then. First derivative of the position function, so we're going to have to take the derivative here, keeping in mind that that omega is a constant, so we're going to have to do the chain rule. So we get negative a omega sine of omega t I plus a omega cosine of omega t j. Then if we want acceleration, we're going to take the derivative of velocity, which is the second derivative of the position function. So here we're going to get negative a omega squared cosine of omega ti, subtract a omega squared sine of omega t times j. Next, we get our F equals ma. Now that we have a, we can plug that in. Our force then is equal to m times that acceleration vector. I can factor out a negative. I have that m, and I'm going to factor out an omega squared. Reason I'm going to do that is that then leaves me with a cosine of omega ti plus a sine of omega t times j. So what we get then is our force vector is negative m omega squared all multiplied by our position function. Okay, so what this is telling us, omega squared is obviously positive. M is mass, that's positive. So our force vector is going to be opposite of the radius vector. So this radius vector that we have right here, the force will be coming in the opposite direction. Since the radius is always away from the origin, the force will always be acting towards the origin. That make sense?
Can you please repeat how you got from the second of the last line to the dot product?
It's not dot product,
Oh,
it's
it's
multiplying.
Oh, okay.
Yeah. Anything else? Alex?
We got a question like this on the test. Do we have to do the last simplification, or can we just leave it like that?
Like, do you have to do this?
Yes.
You could leave it like that. I would expect either way a sentence to tell me what that means. Okay. Keep going?
Yes.
Okay. The next page and a half is just straight up physics. Okay? Next thing we need to talk about, projectile motion. These formulas are going to be formulas that you've seen before. We're going to go through the derivation though. So in the case of projectile motion, we are still looking at Newton's second law. So that F equals ma. There's some assumptions that we're going to be working with. First assumption is that the mass is constant. Second assumption I want us to work with is that the only force acting on the object after its launch is Earth's gravity. Lastly, we are going to assume that the force of gravity is constant. Because the object is sufficiently close to Earth. Okay, so basically here's what's going on. We have the ground, we have some object, and that object is going to follow a path where maybe it goes up, and then eventually it comes back down to the ground. M is going to be the mass. G is going to represent the acceleration due to gravity. Okay, so here's what we know. We're going to start out with the force is equal to negative mg times j. So negative because the object is moving down. We need to take into account the mass and the acceleration. Now, we wrote above that F equals ma. So that F now we're going to replace by ma. And then if I divide by m, I get the acceleration is equal to negative g times j. Okay, we want the velocity. So we are going to have to integrate acceleration. So we are integrating that negative g, j in respect to t. When we do that, we get negative g t j plus c1, remembering that c1 is a vector. Now there's a few things we know on this figure that I haven't written yet. A few things we need to take into account. 1 is the initial height. That has to do with position, so that doesn't help us yet. And then we have the initial velocity. That is what's going to help us now to find C1. So we know at t equals 0, the velocity is v sub 0. That tells us then that C1 equals v sub 0. So, first important formula is velocity is negative g t j, add the initial velocity vector. Okay. Then, if we want to find the position function, we're going to have to integrate velocity. If we integrate this right here, we're going to get negative 1/2 g t squared j plus initial velocity vector times t plus c2 Now we're going to need to use that initial position. We know at t equals 0, the initial position is s sub 0, which is actually a vector. I'm going to write it like that. Okay, so we get C2 is equal to S0 times J. J just meaning that it's moving up. So next thing we know is that initial position function, bringing together the J's, so this one and this one, is negative 1/2 gt squared plus s sub 0 times j plus t times v sub 0. Those of you in physics, did you go through this derivation? Not really. Similar? Okay. We're going to go on and find something a little bit more helpful than these two. Specifically, rather than looking at general velocity and general position, oftentimes we're interested in the position in a specific direction, so in the x direction or the y direction, and we're also interested in velocity in a specific direction, so velocity in the x direction or the y direction. So parametrically, here's what we're looking at. If this is our velocity, if we create this little triangle here, and this is our angle alpha, like that. This side will then be v times the cosine of alpha. This side will be v times the sine of alpha. So that v naught then, another way to express it is the sum of these two vectors. So it'll be v naught cosine of alpha I plus v naught sine of alpha j. Going back to our r of t then, we're going to replace the v naught with all of that. So we get negative 1/2 gt squared plus s sub 0 times j plus t times v naught, which is all of that, what you want to do then is you want to combine like terms. So you want to get all the i's together, all the j's together. Only I term is right here. So that'll be v naught cosine of alpha t I. J terms, there's that j term and that j term over there. So I'm going to write things in a different order. S sub naught plus v naught sine of alpha times t minus 1/2 gt squared times j. That leads us to our two positions. So parametrically, that is our x equation, that is our y equation. So you might be asked about the position in a specific direction, in which case these are the two equations that you're going to use. Which leads us to the velocity in each direction, if we take the derivative of both of those. So take the derivative here. Remember, this is a whole constant on t. So you're going to get v naught cosine of alpha. Velocity in the y direction, that'll go away. This is a constant on t, so that'll be v naught sine of alpha. Take the derivative with respect to t, so minus gt. So those two give us the velocity in each direction. Okay. We have one example to do. Sound good? Okay, it's multi-part though. The baseball is hit with initial speed of 80 feet per second at an angle of 30 degrees with an initial height of 3 feet. Part A, I want us to find the parametric equations for the trajectory of the ball. Okay, that 30 degrees, that's our alpha. That 80, what is that? V naught, yeah. It's our initial speed. 3 is the S naught, the initial height. So for x, using this formula, we get 80 cosine of 30 times t. Cosine of 30? Root 3 over 2. So our x ends up being 40 root 3 times t. Our y, again using that formula that you guys wrote down, is 3 add 80 sine of 30 t minus 1/2. What's g? Huh? What's the value of g? Feet. 32? Right, 32 feet per second. Sure? Okay, great. You guys are supposed to be the ones that are good at physics here, not me. Oh. Well, I'm going to tell you next semester, all the units that you guys use in physics, we're going to give them all new names, just so you know. I don't know why. I don't know why in Diffie-Hughes we use different units than you guys do. But anyway, those are our two parametric equations. Okay, part B. How high does the ball get? So how high the ball gets, that has to do with y, has nothing to do with x. So we need to find the maximum of y, the maximum height. So you're going to take the derivative with respect to y. Derivative of that right there. So we get 40 minus 32t. Any extrema are going to happen when the derivative is 0 or undefined. If I set that equal to 0, I get t to be 5 over 4 seconds. Okay, if I plug in 5 over 4, I get 28 feet. Now, I want you to show that this is in fact the maximum. So it has to be because that's the only critical point. How do I find that this is in fact a maximum or prove that it is the maximum? First derivative test? Yeah, so I think last year in BC, you guys had to like write a sentence maybe. I don't care that you write the sentence. If you show me the number line and show this is negative, that's positive. Nope, that way. That's fine with me. So show that and show, yep, it's a maximum. That's all I care about. Don't have to write me a sentence. Okay, 2 more. How far does the object travel horizontally? So we need to know when our x is 0, when the object is back on the ground. I'm assuming you guys can solve that just fine. Yeah, great. I'll tell you it ends up being 2.57 seconds. Sorry, this is y. So when y is 0, the ball is on the ground. What you want to do then is plug that 2.57 into x, and that tells you the x position when the ball is on the ground. I'll tell you it ends up being about 178.25 feet. And last question. What is the speed of the ball when it lands? So it lands, we talked about when the time is 2.57. Speed we also talked about is the norm of the velocity vector. Velocity vector we haven't found yet. It's the derivative of position. We found the position. If you take the derivative, you get 40 root 3, comma 40 minus 32t. Our speed then. Norm of this when we plug in 2.57. So it'll be 40 root 3 squared, and then 40 minus 32 times 2.57, that whole quantity squared. If you trust me, that's about 81.19 feet per second. Okay, that's projectile motion. Any questions on projectile?